All right, well, let's go over the answers to that activity that you had to do, and you had to open up that, I don't know if I say it right, but pHet website, and you had to work with friction this time. Last time you had to work with force, and you had the people pulling on the rope in opposite directions. There were red people and blue people. Well, this time you're working with friction in regards to moving some objects around. So let's go through this. It started with question number 10 on there, because I separated the two worksheets actually, but I said set your friction bar medium, select one 50 kilogram crate, and slowly apply a rightward force using the single arrow button. So you're slowly trying to push it to the right. And question letter 10, letter A said stop when applied force reaches 10 newtons. So you should have gotten it up to 10 newtons. What is the friction force? Well, the friction force should have been 10 newtons also. So you're pushing with 10 newtons of force, and the friction is exerting 10 newtons of force back on you, right? What's the sum of the two forces? All right, we got two forces going this direction. One is you pushing, the other one's friction going back, and it should have been 0. All right, so 10 newtons in each direction, they cancel each other out. And then the third one is the crate accelerating. Is it speeding up, slowing down, or changing direction? Nope, it's not. So we're not getting any acceleration because what do I have? I have a balanced force. And if you remember balanced force, remember the idea of that tug of war. With a balanced force, there's no motion. The rope doesn't go in either direction. It just sits there, right? So I've got 10 newtons in one direction and friction's exerting 10 newtons in the other direction, and it's not going nowhere, right? So I go to 10 letter B. Now stop this time, you press the arrow button, you stop when you apply the force of 100 newtons. So you increased your force, so you're pushing even harder on that crate. First one, what is the friction force? The friction force says it should have said 100 newtons. So you're pushing with 100 newtons. The friction on the box is exerting with 100 newtons. Second one, what's the sum of the forces? 0 again. All right, they cancel each other out again. And then the third one is the crate accelerate. Is it speeding up, slowing down, or changing direction? Nope, still not. You're still not getting it to move because you're still not exerting more force than the friction. We've still got a balanced force, so I'm not getting any motion. So now we go to letter C. This time you're supposed to stop when you apply the force that reaches 200 newtons. So you raised your amount of force. You're pushing even harder on that box. So now letter I, the first one, what's the friction force? So the friction force should have been 94 newtons. All right. Second one, what is the sum of the forces in which direction? Oh, wait, I'm pushing with 200 in this direction, and the crate is pushing back with 94, which is smaller. So I end up with a greater force of 106 newtons going in the direction that the box is moving. Okay. So now question number 3, is the crate accelerating? Is it speeding up, slowing down, changing direction? Yes, because I'm creating more force than there is friction. So the crate is actually speeding up, and you should have found that it was speeding up and going in the one direction that I was pushing on it, or you were pushing on it, or the guy on the computer was pushing on it. Right. So we are actually causing it to move because we have a net force. It's not a balanced force anymore. It's not equal in both directions. Now I've got more force in one direction than I do in the other, and the object starts to accelerate in the direction of that greater force. All right, part letter D. Now move the applied force back down below 50 newtons, but above 0. So you had to put it below 50, but somewhere above 0. So somewhere in that range. All right. So what was the friction force? You should have found that it was less than 50 at that point. All right. And question number 2, what's the sum of the forces in that direction? 0 again. Uh-oh, it's 0. Is the crate accelerating, speeding up, slowing down, or changing direction? Nope, it wasn't. All right. Because now you had a balanced force again. All right, number 11, what happens to the box when the frictional force is greater than the applied force? If that frictional force is greater, then there's no movement, right? Because then we end up with a balanced force. The friction force is going to push back with the same amount of force that you push forward, and we don't end up with any motion when it's balanced. Right. Number 12, compare the applied force required to move a 50 kilogram crate and the applied force required to move something much more massive, like the 200 kilogram refrigerator. So the first one, you should have tried the 50 kilogram crate. What amount of force did it take in order to get it to move? You should have found it was the least amount of force, right? So a low amount of force to get that 50 kilogram crate to move. Letter B, now when you replace that and put the refrigerator up there, which is 200 kilograms, you should have found that took even more force in order to get it moved. So you had to push with a gob of force to try and get that refrigerator to finally move. Now, why? Because there's greater frictional force on that bigger object. It's got greater mass, so it's going to have a greater friction. Remember what we talked about in the notes the other day, that Ford Motor Company used aluminum in order to decrease that mass, which decreases the frictional force, which makes it so it doesn't have to exert as much force in order to get it to go, so they could get better gas mileage with their vehicles. Right? Same idea with this. That 200 kilogram refrigerator is going to exert a lot more force than a 50 kilogram crate. All right, number 13. Compare the applied force required to move a 50 kilogram crate when there is lots of friction. And then medium friction, and then no friction. So lots of friction, that means we've got this thing sitting in like a parking lot, a dirt parking lot where it's really, really rough, right? And you're going to try and shove this crate on something that's really, really rough. There's a whole bunch of like bumps all over the place. Not saying it's stones, because that would give me like wheels, but I'm talking like something that's really, really rough. You should find that it took a whole lot of force, and what I found was 300 newtons to finally get it to accelerate if you had lots and lots and lots of friction applied to that. When you changed it to medium friction, so now we're talking like, let's say like the gym floor, which is really, really smooth, so it doesn't have lots of friction on it. And you were to try to, not a great idea because it's going to scratch the floor, but you try and push that crate across the gym floor where it's really, really smooth, it should have taken a lot less. And I had down, it took 15 newtons to accelerate it. So it didn't take as many newtons to try and get it to move. And then you have no friction, none. That would be like it's sitting on ice on a roadway after we've had an ice storm. Right? Does it take very much force in order to get that crate to move if there's no friction and it's really, really icy? No, I had down, it took 1 newton barely. Like as soon as you clicked the arrow and got 1 newton, the crate started to move. And think about the idea that even at our school, what's the kind of weather that definitely almost always will close our school? And I know you're going to go, well, we don't ever close. Yeah, we do. You got to look back. We have closed. Do we close because we get lots and lots and lots of snow? No, not usually. We can if we get a bunch of snow and they can't get the roads cleared. But snow doesn't really cause the school to close. What really causes the school to close is if we get ice. If the snow is really, really icy, or we get an ice storm. Now, why is that? Because just like this activity here, ice, no friction, it doesn't matter how big the tires are on the buses, doesn't matter how big the tires are on the monster truck. If it doesn't have any friction, then it doesn't have any force, or it doesn't take much force for it to like go all over the place, and it makes it a whole lot harder to control. So we end up having to close if it's really, really icy, because we can't control the buses out on the roadway. And people that are trying to get to school driving their cars can't control their cars on the road. So it's something to remember in the future. If you get an ice storm, and this could be 20 years from now, and all of a sudden there's a really bad ice storm, it's probably best place to be, stay home. All right, stay home until the ice is cleared off the road, whether it's cleared off by the road commission with salt and their scrapers, or you wait until it warms up in the daytime and the sun starts shining down and it starts to melt that way, because we raised the temperature and got the ice to melt. That's probably the best thing to do, because even as you notice on this, even going slow on ice, it's not going to be good, because inertia, your car is just going to want to go straight. And you press on the brakes and try and apply friction to your car to try and stop it, there's not going to be enough friction to get your car to stop. And your car is going to keep going. And that's why we end up with so many accidents when it's icy out, because it's really almost impossible to control your car. And again, doesn't matter whether you got big old monster truck tires on your truck, that doesn't help. Right? The only thing that will help is if you put chains on your tire. But I will tell you, having been an old driver's ed teacher, chains in Michigan are illegal. You can't put chains on your tires in Michigan because it wrecks the roads. So the best thing to do, stay home and make up some hot chocolate, go outside and play in the ice and snow, and enjoy the cold weather while we have it. So have a great day. We'll see you.